Okay, so we're continuing with our example of a correlation and the least square regression line with the diner that's selling hot oatmeal on cold mornings. And we've already created the scatter plot. The scatter plot shows us that as the daily temperature drops or actually gets higher, as X gets higher, increases, that the number of bowls of oatmeal sold decreases. So on the colder mornings, more oatmeal is sold than the warmer mornings. We've already done 8 steps of this process. Today we're going to start with step 9. So I'll be back to referring to this scatter plot in a moment, but let's look at what step 9 says. Now you have a list of steps. It only looks slightly different than this because I gave myself some room to write. But we're going to, in step 9, it says, using the graphing calculator, find the mean of each variable and plot the point x bar, comma, y bar. Okay, so what is x bar? I mean, not the number, but what is it? What does that mean? X with bar on top. Anybody? It's the average. Okay, so x bar is the average of the x's. 2 ways to do this. You can just take your list of x's and add them up and divide by how many there are, and you'll have x bar. Or if you want to let the graphing calculator help you out a little bit, we can experience that again by entering, okay, if your lists are in there, you can get this with the calculator. So we're going to hit Stat, Calc, and I'm going to arrow down to 2 and do 2 variable stats. Okay, this is just going to get us statistics on both sets of data. So you hit Enter, and then you tell it which list you need. So if you put it in list 1 and list 2, then you're going to go second and the number 1, comma key, which is just over the number 7, and then second and the number 2. When you've got this on there, hit Enter, and you're going to get a whole lot of data here. This arrow tells us that there's a lot down below. So go ahead and record your x bar. We'll say that x bar here is the average of the low temperatures, and that is 36 degrees. Y bar, I'm going to arrow down, and you'll see all of it. Okay, there's y bar. And y bar is the average of the y's, and that's 12. Okay, so x bar, y bar. Now, looking back again at what it says in number 9, we are going to use this, we're going to plot this point, okay, and plot the point. All right, so this becomes a point on our scatter plot here. And this is actually going to be a point that's on the least square regression line. And therefore, we'll need to get some other points on there. But let's get that point on there first. Let's see, I'm going to go to red. Okay. 36, 12. So out 36, up 12. Right there. So that's the x bar, y bar point, right in the middle of all those points. The average of the x's and the average of the y's. So it's right smack in the middle. All right, now let's talk about the slope. Because in number 9, I say that we are going to use the slope to determine a couple of other points on the grid that are on the least square regression line. So, you know, in the past when you did Algebra 1, you had a point and on a line, and then you use the slope by going rise over run to find another point, right? Everybody remember that? So we do have the difficulty of our slope not being a simple slope, like 2/3 or something. Does anybody have that information written down somewhere? What the slope of this line is? Yes, it's negative 0.66. Okay, so this is the information that came off the graphing calculator when you did your linear regression. Okay, so we've taken this and turned it into a fraction, negative 0.66 over 1, so that we have a rise over run. So now I'm going to make another suggestion. Okay, you don't have to do this every time. It might be helpful every time, and it might be that you want to use even a different number than what I'm about to do. I want to make this a little bit easier to manage on the scatter plot, because the scatter plot, everything is very close together here. Okay, so 1 unit away is like half the box, and making it a little bit too close together to deal with. So I'm going to multiply both the top and the bottom of this fraction, the numerator and the denominator, by 10 over 10. 10 over 10, what is that? It equals 1. So I'm not changing anything about this. Okay, I'm still keeping the same value. So by doing that, I've changed the numbers a little bit. So now we have negative 6.6 and over 10. This is just going to be an easier rise over run. Now, some of your data sets, if they're in the hundreds, it might be better to multiply by 100. And that way, if you've made little blocks that are 100 wide, then it's going to be much easier to count by hundreds than it would be by 1. Okay, so the reason we're doing this is just to have an easy rise over run. All right, so our rise over run is down negative 6.6 to the right 10. So from the point that we've put on here, our X bar, Y bar point, we're going to go down 6 units and almost a seventh. So remember, these are by 2s. So 2, 4, 6, and almost 7. Okay, I'm going to keep that position, and then I'm going to go to the right 10. 2, 4, 6, 8, 10. And make another point. Now remember also, you can always change the sign. So 6.6 over negative 10, same thing, just gives us the ability to go up and to the left. So again, we're going to go up 2, 4, 6, and almost 7, and then to the left 2, 4, 6, 8, 10. Now I have 3 nice points all in a line that I'm going to connect to make our least square regression line. So all the work that we did prior, where we dealt with this equation and plugged in the values, remember at some point you have y hat equals negative 0.66x plus 35.7. Okay, that was step 8, I believe, where we wrote down the least square regression line. Well, now we know where that line actually is. What was the y-intercept on this?
35.7.
The 35.7 is the y-intercept, so let's take a look and see where that's going to fall. Remember that sometimes your scatter plot is not going to have the y-axis there for you to see where that intercept is. In this case, because we have the origin here on the plot, we can see it, and if we go up a little bit more, it would have fallen right about there, and you could see that that really kind of is in line with the rest of the points. So we're going to connect these points and have the least square regression line on our plot. Now we use this least square regression line. Now notice a couple of things. If I made the plot a little bit bigger, it probably wouldn't have touched any of the points. It's kind of touching a couple of them, but generally speaking, it's like in between all the points, which is what it should be. It should be between all of the points and not necessarily touching any of the points. Okay. that line needs to be on each one of your plots. And number 9 tells you how to get that line on your plots. Okay, number 10. Number 10 says we're going to choose a value within the range of the given explanatory variables and interpolate. Then we are going to write a sentence interpreting our prediction. Interpolating is a prediction. Okay, remember when I told you that y hat is a prediction. That stands for we're predicting what y will be when there is a certain x that we choose. So we're going to be using this equation for the next couple of problems. So I'm going to write it again right here. Y hat equals negative 0.66x plus 35.7. Okay. When I say I want within the range of the explanatory variables, okay, go back, look at your list of variables. Which one's the explanatory variable? The low temperature is the explanatory variable, and the range goes from a low of 25 to a high of 50. So I need a value. I'm just going to pick a value, okay? You are going to pick a value in your data set that you want to make this prediction with. Don't pick one that's already there. Okay, so picking one in between here, I'm going to pick what happens when it is, how much? 33 degrees? That's right in between two of them. Seems reasonable. Okay, we're going to pick 33 degrees. So when I say I'm picking 33 degrees, that's x. So x is going to equal 33 degrees. Now, what do you think I'm going to do with that? What just happened? So what do you think I'm going to do with that x, 33 degrees?
Plug it into the equation.
I am going to plug it into the equation, exactly. So we have y hat equals negative 0.66 times 33 plus 35.7. So now I'm just going to do a little math here and find out what y hat is. Step 10. So on your calculator, or no other way to do this besides actually plugging it into your calculator. And I get 13.92 degrees. It's not degrees though. What is it?
Bowls.
Bowls of oatmeal. So about 14 bowls of oatmeal then. So I say write a sentence interpreting your prediction, and that sentence would be when the low temperature is 33 degrees, about 14 bowls of oatmeal will be sold. Let's take a look at how that looks on the scatter plot to see if that matches the line. So if we look at 33 degrees and we go up to see where that line is, it's right at 14. How perfect that is. So that confirms that our line is really good, 33 degrees up to about 14. Our line is really good. And we correctly did that little bit of math. And that's the interpretation. Now, again, it's an interpolation because we picked a value within the range of the data. So number 11 is going to work the same way, except that we are extrapolating. And extrapolating is choosing a value outside the range of the values that are the explanatory variable, the x values. Okay, again, our range goes from 25 to 50. So I'm going to pick 10 this time. What happens when it's 10 degrees? So using that same equation up there, this time I'm picking, and this is what you'll have to do with your problems, you'll have to choose a value. I'm picking that we have what's happening on a day that's 10 degrees. Okay, so this owner of the diner he knows next week there's gonna be a lot of low temperatures around 10 degrees, so he wants to know how much oatmeal he needs. So, again, we just plug it right in. Negative 0.66 times 10 plus 35.7, and our prediction will be how much? 29.1. You try to do that in your head? Good. Good exercise. So 29.1, or about 29 bowls of oatmeal will be sold each day that the low temperature is 10 degrees. So again, same sentence, different numbers. When the low temperature is 10 degrees, about 29 bowls of oatmeal will be sold. Okay. Again, just taking a look at the scatter plot for 10-degree days, 10 degrees, all the way up, and yeah, it's about, getting about 30 up there at the top. 29. So our plot is confirming our answer with the equation. You should check that every time. Now the number 12, we're gonna look at the plot again and do some analysis in regard to the plot. Sometimes you're gonna see when you start getting your least square regression line in to the problems that were assigned to you, you're going to see the points will be scattered all around that line. In this particular case, the points are pretty close to the line. I want an analysis of the point that is farthest away from the line, and by farthest away I mean vertically, up and down. So can somebody identify what that point is that is farthest away from the line vertically? 3410. So it's this one right here. Let me pick another color. Don't show up any. 3410 is the point that's farthest away from the line. It's below the line. This one's a little bit, but I think it's closer. This is definitely the farthest away. So how do you identify that? You pick it out which one's the farthest away. Then you just have to identify that point. Even if you have to go back to your table, okay, we could see that it hit 34, and then 3410 on the table is the actual point. So if you can't quite read your graph for some reason or another, go back to the table, and these points that were originally here come from your table. So 3410 is our point that is farthest away. Okay, I'm going to write that down here, 3410. Remember that points are X and Y. There's a little formula that I thought I had written down here. Okay, here's the formula. You need to write this down. Simply Y minus Y hat. Okay, I do have it on your list. Okay, for whatever reason it didn't print on mine. So this little formula is on your list of steps. Y minus Y hat. Okay, we know what Y hat is. We've been doing Y. We've just done 2 problems with Y hat. This Y comes from the point that we just discovered. Okay, so this Y is going to be 10. Y hat we now have to calculate. So we calculate Y hat by doing that formula up there. So which is Y hat equals negative 0.66 we're going to use this x, 34, times 34, plus 35.7. So all I did was substitute y hat, that we just, the same equation that we've been using, and put in the x value here. Remember, this is x, and this is y from that point that we picked. And then subtract that from 10. So we have 10 minus the 13.26. Okay, and so the answer, or be careful, it's negative, is negative 3.26. And it's negative because it's below the line. So that negative is telling us a distance here, above or below the line. So if you pick a point that's above the line, your residual value or your distance is going to be positive versus negative. Depends on which point you pick. So just to clarify here, this little formula is the distance, is a distance. And it has a negative or positive based on above the line or below the line. So that gets us how far away from the line, vertically, the point is that we picked from our least square regression line. All right, so in this particular case, you don't have to write a sentence. Do the math. All right, 2 more steps, guys. We're almost finished with this whole process. Yay. Okay. We're now going to look at this r squared. Again, my computer did not turn that into r squared when it originally was. I think that on your list I actually made that an exponent. Copy and paste it. Didn't move it right. All right, so r squared from our list of data here. Now we've talked about everything but r squared. We know the slope, the y-intercept. We talked about the correlation r, which in this case was very strong, negative correlation. But now we're going to talk about r squared. Obviously, when you square a negative, it becomes a positive. So r squared is always going to be a positive value. R squared is always going to be positive. And since we aren't concerned about the direction anymore, the negative or positiveness of the association or correlation, in this case, we're only concerned about how close it is to 1, or when we're going to turn it into a percentage. So we're going to turn this into a percentage and call it 91%. So r squared is 91%. Now, what is it 91% of? Oh, by the way, I wanted to tell you what r squared is called. R squared is called the coefficient C, and that's another I, coefficient of determination. Sounds very philosophical, doesn't it? Coefficient of determination. Sounds important. That's what they call it. I do not know. So our coefficient of determination is 0.91 or 91%. So we have a sentence to write here. And it's one of those almost a fill-in-the-blank kind of sentence. Okay, so here we go. 91% of the variation in the daily low temperatures can be explained by the linear regression, and that's which is simply the line that we made. Of the number of bowls of oatmeal sold on low temperature. Now, let me explain. First of all, the 91%, you know where that came from. Variation, that is how that varies on the scatter plots, how these temperatures don't all fall on the line. So if they all fell on the line, it would be 100%, there would be no variation. 100% would be explained. But a few of them are falling off the line. So 91% is explained. Now this part right here that I'm about to underline, this is the explanatory variable. Okay, whatever your explanatory variable may be, remember that's X. In words, you fill in the blank with whatever that explanatory variable is. And then the can be explained stays in there by the linear regression of the number of bowls of oatmeal sold is our Y, or response variable. And then again, we mention the X variable. So where I've got the lines, that's where you fill in the blank. So this is R squared is the first one. You turn it into a percentage, of course, move the decimal over twice. 91% of the variation in the daily low temperatures can be explained by the linear regression of the number of bowls of oatmeal sold on the temperature. And the way they phrase that is a way we talk about that linear regression. I know it sounds kind of awkward. My main point here is that you understand that you may see this in a multiple choice question, and when they're talking about this variation and explained by the linear regression of this on that, you know, it's just R squared. It's just R squared. So all you have to do is probably know that when you are filling out, when you are getting a question, a multiple choice question like this. Okay, you got this? All right, we are almost ready to answer a question here that is our conclusion. Back to step 4. So 14 in the conclusion part, it says write a few sentences, statements supporting your opinion in response to the following. We need to go back and answer our causation question in step 4. And then we need to determine whether the best fit line, that's our linear regression, is a good model or predictor for the association between the two variables. Okay, so all of this time and all these steps that we've been doing, we've just been kind of building evidence as to whether that that association is giving us a good model. And the model is another word for that least square regression line. It's an equation. A model in math is an equation where we're modeling something, a pattern that exists. In this case, it's that relationship between the temperature and the oatmeal. So we're modeling it, and we want to know if it's a good model. Okay, so what do you think? Do you think it's a good model? And what do you think we should base that on, whether it's good or not? There's the plot. So what was our causation question here? Does anybody remember? I have it written somewhere.
Does the daily low temperature cause an increase in the number of bowls of oatmeal sold?
Great. Okay, that was our cause. So does it? You think?
Yes.
Yes. I agree with you. So we are going to say, by answering that question, you need to stop a minute and think about what the, how you want to write it. Okay? So think about what your sentence is before you start writing. All right, so first we want to say that we have evidence to support that the daily morning low temperature does affect the number of bowls of cereal sold, oatmeal sold. Okay, so that kind of thing. So what did I say? There is evidence to support there's evidence, I'm gonna get rid of to support, that the daily low temperature affects the number of bowls of oatmeal sold. Okay, so that answers the causation question. We want to know if the model's good, so we need to say something about why we think the model is good. One of the reasons should be your R and your R squared. Okay, because, probably shouldn't start a sentence with because, somebody probably should correct me on that. Because the correlation coefficient and the coefficient, these are all fancy words for you, of determination are high, or you could say strong. The model, and you can even say what that is, y hat equals negative 0.66x plus 35.7. Remember, a model is an actual equation. Is a good predictor. So, mention something about R and R squared. Mention something about the model being a good predictor. If it had been a bad predictor, okay, then when we found those numbers, they wouldn't have matched on the equation, on the line very well. Those numbers that we put into this wouldn't have matched up with the line or with the other points. They would have been far away from the other points and might not have, would indicate that it's not such a good model. So to have a good model, you have to have a strong R, a high coefficient of determination percentage, and it needs to be a good fit when you do the prediction. It needs to fit with the other points on the graph. If it doesn't fit, then it's not such a good model.